Hello everyone, this is video 12.9. We're going to be looking at using the moving and additivity principles to prove the Pythagorean theorem. I guess as an extension of this, we're going to define the Pythagorean theorem. It's not something that we really looked at or talked about so far this semester, so we're going to introduce it and then talk about the proof. Let's get started. So the Pythagorean theorem is about the relationship of the sides or the side lengths in a right triangle. This is specifically something about a right triangle. This does not apply to triangles which are not right triangles. That is a very important distinction. Students will sometimes try to apply this to triangles which are not right triangles, and that just simply doesn't work. Um, there are uh, there are ways that we can use other formulas which apply to triangles which are not right triangles, which are very similar to the Pythagorean theorem. If you're curious about learning about the law of cosines, knock yourself out. We're not going to cover that in this class. But there are things which are very similar to the Pythagorean theorem, which apply to triangles which are not right triangles. But all we're doing in this class is Pythagorean theorem for right triangles. That's it. As a little bit of a reminder, we haven't used these terms in a while. By a right triangle, we mean a triangle that contains a right angle. Simple as that. We know it can't contain more than one right angle. We had this question before, because a right angle is 90 degrees. So two right angles would be 180 degrees, and the triangle can only contain 180 degrees. So that would mean the third angle would have to be 0, which doesn't make for a very interesting triangle. So we know we're only going to have one right angle. The hypotenuse is the name we give to the side that is opposite the right angle. So if we draw a right triangle like this, so here's my right angle. So this side over here we refer to as our hypotenuse. And this is going to come up in a little bit, but these two sides over here we generally call the legs of the triangle, which is a little confusing because sometimes you'll see in an isosceles triangle the two congruent sides also being referred to as the legs. So yeah, when we're talking about a right triangle, legs has a specific context, and isosceles triangle it has a different context. We also want to define this idea of a theorem, which we talked about before. We haven't seen this word in a while, but by a theorem, what we mean is it's a provable idea in mathematics. When we mentioned this before, we made the distinction between a theorem, which is something that we can prove, and an axiom, which is something which we just assume. It's true because we take it to be true, or we're given that it is true. So axioms are typically not things that are provable, or that need to be proven, or even really have a proof. They're just statements that we use foundationally, whereas a theorem, like the Pythagorean theorem, is something which can be proven. So the Pythagorean theorem, and this is taken directly from the book here, it says that in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the other two sides. Now, I would highly recommend that neither you nor your students memorize that word for word. I mean, more importantly is that we understand sort of what it says and the idea behind it. Memorizing that verbatim is not really a top priority. Now, at the same time, a lot of people, if you ask them what is the Pythagorean theorem, they'll say a squared plus b squared equals c squared, which is just the formula, but without any real context. And so you've got this sort of verbal written form, which is not really very convenient or very wieldy, which I'm going to kind of like push you away from a little bit. And then you have just the formula, which is also limited because we don't sometimes understand everything that's going on in the formula. And students who just sort of memorize a squared plus b squared equals c squared may not really understand what this is saying. So, like everything else we've really talked about in this class, we've got this sort of concrete foundational idea, and then we have this abstracted formulaic form. And the real understanding is going to be in connecting the two ideas. that we see the formula and know what it means and know what it represents and know sort of how to talk about it. So we'll look at a third form of this in a moment, which helps sort of pull all these ideas together. But if we look at what the formula says here in a right triangle, the square of the length of the hypotenuse. So this is my c squared. This is my hypotenuse squared. And so my hypotenuse is my c, which is what we have here. And then is equal to the sum. So we've got my sum here. The squares of the lengths of the other two sides. And so these are my other two sides. These are the legs of the right triangle. And then each of those gets squared. And so we've got side A squared, and then we've got side B squared. And we're going to take the sum of those, and that will equal the hypotenuse squared. So in some books, you'll even see it written out sort of in this form where we've got side A squared plus side B squared equals hypotenuse squared. And so it's written out sort of in a combination of formula and verbal and words. And then the words are replaced with the algebraic symbols, and we get the a squared plus b squared equals c squared. The point is, I want to, like I said, really discourage you from either making students memorize word for word that definition, but more importantly and sort of more commonly, really try to discourage you from having students just memorize a squared plus b squared equals c squared without really understanding what those letters represent. Now, the why does it work? That's a separate question we'll come to in a moment. But again, just memorizing a formula devoid of any real context or meaning is what we're trying to avoid. So I like this picture a lot for a couple of reasons. Number one, we're talking about the square of the hypotenuse and the square of the other two sides. And so we can talk about square as something numeric, like the square of 5 is 25. But we can also see the square as something geometric. And so this is my right triangle here, ABC. This is my triangle here. And so the side AC, which is my hypotenuse, because it's opposite this right angle here, well, it has a length of 5. And we can see it has a length of 5 because we can count 1, 2, 3, 4, 5. And so the square of 5 would be 25. And so we can show that by constructing this square on this side length. And so we can see this, this 25 right here. And then over here, this BC, well, it has a length of 3. And so we can show that square by making this 3 by 3 square. And so this is 9. And then we've got this AB here, which has a length of 4, obviously. And so we get that 4 by 4 squared. And so we mentioned on the previous slide, we have this sort of verbal form and we have this symbolic form of the Pythagorean theorem. But this pictorial form, this geometric form, is, I think, crucially important. And it can serve as sort of a bridge between that verbal form and that formulaic form. I think if you read both of those, it's hard to really understand what's going on. But once you see the picture helps sort of illuminate both of those two forms. It just makes them make a little bit more sense. And so all three of these forms of the Pythagorean theorem, that written form, the symbolic form, and this pictorial form, all three work together to give a really clear picture, or at least a clearer picture, of what the Pythagorean theorem is. There's some other ways we can approach it, like what's a real world example? How could we use the Pythagorean theorem in an actual application? And there's some other ways that we can talk about it. But I think these three give us a good starting point for understanding the Pythagorean theorem. Like I said, this also gives us a clear sense of what the squares kind of mean and how they work together. And if we wanted to, we could even sort of like take these 3 by 3, these 9 pieces here, and color in 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we can see how these 9 come up here. And then if I do these in blue, we can see this is 5 by 3, so this is 15, 16. It's been my experience that we talk about adding these two squares together, like exactly how those squares add together is not always entirely obvious for students. And so the fact that these 16 plus these 9, let me switch back to red, plus these 9 make this 25, for some students to see how these two squares can be taken apart and put back together into one square is a powerful process. I mean, it's a like, especially if they do it kinesthetically. I mean, if they actually move the pieces around and see how they reform into this one larger square. Um, we talk about these things sometimes like students just understand what this process is and what it means, but actually doing it and seeing it and constructing it gives an extra layer to this understanding of what the Pythagorean theorem is. The last thing I like about this picture so much is that it shows this nice 3, 4, 5. Um, if you just pick two numbers at random and put in the Pythagorean theorem, odds are you're probably going to get something that involves a square root as your third number. So um, if you were to take the legs to be length 1 and length 1, then your hypotenuse is going to be square root of 2. Working with students sometimes, especially if they're working around square roots, is a little bit shaky. If you're trying to focus on the Pythagorean theorem, you may want to put square roots to the side until students understand how to use and work with Pythagorean theorem. And now, once their understanding of the Pythagorean theorem is a little bit more solidified, now we start to do problems that involve square roots. So, knowing a lot of Pythagorean triples, um, and by that I mean three integer values that fit well with the Pythagorean theorem, that work with the Pythagorean theorem, um, allows you to work with the theorem without having to work with square roots. And so 3, 4, 5 is a pretty nice, pretty basic one. There's an infinite number of others, but we'll talk about that a little bit more later on in the video. But 3, 4, 5 is a nice one to have in your back pocket to work with and to give examples with. I do want to point out, though, and this was mentioned in the 12.8 video as well, that this figure is not a proof. Um, this figure only shows one specific example. And so I could use this example to disprove something, to show how something is not the case. But if I want to show that the Pythagorean theorem actually works, I can't just say, well, here's this 3, 4, 5. It fits, therefore it always works. There's a big step between it works in this case and it works in all cases. So if I want to do a proof, I really need to show that it works in a general case, that it will always work for any right triangle. I know that if I measure the sides, this relationship still holds. Um, so that's a different level. Now, ironically, um, the section doesn't really do the proof. The title of the section is that we're going to use the movement and addition properties to do the proof, and yet the section never does the proof. The proof is actually an activity that we're going to do in class. So it's a little bit of bait and switch, a little bit. And there's about a gazillion different proofs of the Pythagorean theorem. And so if you go online, you look at any number of online resources, and you type in Pythagorean theorem proof, you're going to find a bunch of different ones. And the one that you find may not be the one that we're going to do in class. So depending on the complexity of some of the proofs, and to be honest, some of the proofs are not really fantastic proofs. They sort of convince more than they actually prove. The one that we're going to do in class is really going to prove it pretty rigorously. Um, so, depending on the level of the students, you can decide how much proof you think is appropriate. You want to do as much proof as the students can handle, because we want to approach this topic with as much rigor as we can. But depending on the level, it's okay to do a little bit more proof that convinces and less proof that proves. The last thing that I want to say about the Pythagorean theorem is this idea of the converse of the Pythagorean theorem. Now, the converse means that we're going to switch the order of the two statements. Sometimes people mistakenly call this the inverse when switching them up. The inverse is where you would take the negation of both. You would say if something is not the case, then the other thing is not the case. We're not introducing any nots. We're not saying anything isn't the case. We're just switching the order. So to clarify what I'm saying here, the Pythagorean theorem says if it is a right triangle, so this is my first statement here, if it is a right triangle, then the side length relationship a squared plus b squared equals c squared exists. So I know that my relationship here holds. The converse then is going to be to switch these two things up. And so now if the side length relationship exists, then we know that it's a right triangle. And so an example of that might be if we're given a triangle and let's say we know the side lengths are 5, 12, and 13. The question might be, well, is this a right triangle? And so now, unlike the first problems where we were given it was a right triangle and we used that to find a missing side, now we have the three sides. We're given the three sides, but we want to know if it is a right triangle. And so we look at these three sides and we're going to test it out. Well, we know this would be the hypotenuse because it's the longest side. And it's opposite what we suspect is the right angle. So, I mean, this looks like the only real candidate to be the right angle here. And, like I said, it's also the longest side. So I know we're going to have to check, is 13 squared equal to 5 squared plus 12 squared? So I'm going to test out this side relationship and see if it works. And we get 169 equals 25 plus 144. And sure enough, we get 169 equals 169. This works. So because the side relationship works, now I can say this is absolutely a right triangle. And so now we know this is a right triangle. If we were to try another case, if we were to try, say, 5, 11, and 13, then we would get 169 equals 121 plus 25. That's 169 equals 146. Wait, that doesn't work. So because the side relationship doesn't work for this triangle, we know that it's not a right triangle. So we can use this relationship in both directions. It works both ways. The normal direction, the Pythagorean theorem, if it's a right triangle, then this relationship exists. And then if we switch it around, that's called the converse. If we can show the side relationship exists, then we know it's a right triangle. We're not going to do a whole lot more with this. It's just I think it's important that you see that this statement works in both directions. Okay, so for your checkpoint, this is a little bit bigger of a problem here. I showed you the 3, 4, 5 will work in the Pythagorean theorem, so it is a Pythagorean triple, as it's called. So what if we add a constant amount? So example, if we add 1 to each of those numbers, and now we get 4, 5, 6. Does that work in the Pythagorean theorem? If we add 2 and get 5, 6, 7, does that work for the Pythagorean theorem? So can I add a constant amount and have that always be a Pythagorean triple? Part 2 to this question is, what if we multiply these numbers by some constant amount? So 3 times 2, 4 times 2, 5 times 2. So if I take 6, 8, and 10, does that work for the Pythagorean theorem? If I multiply them all by 3, multiply them all by 5, does that seem to work? So work through some cases of adding and of not adding. And this question is good because it'll get you thinking about two things. Number one, it gets you practicing the Pythagorean theorem, which is kind of the point of the section. But it's also good because it also will allow us to talk about how we think about proof as well, and what's required to prove something, and also what's required to disprove something. So if you have any questions about this problem or anything else from this video or this section, as always, bring your questions to class and we'll get them answered. All right, thanks.